The ratio test, extremely important. That's why we got underlined a little bit of mulberry up in there, right? Extremely important. We're going to use this quite a bit in the future as well. But the ratio test and the root test, two videos very closely connected. The memorization part is the same. Less than one converge, greater than one diverge, equals one inconclusive. That's going to be the same for the ratio test and the root test. The ratio test works in a lot of different scenarios. The ratio and the root test both work whether it's an alternating series or whether it's not an alternating series. So there are certain things that happen in the problem that basically say, hey, I'm going to use the ratio test on this problem. So just because I see the alternating series doesn't necessarily mean I'm going to use the alternating series test, right? So the ratio test is perfect for anything that involving factorials or a sequence type problem, which I'll show you in a second, or some sort of weird combo with like n powers, right? I got an example of each. So what I'm saying is sometimes you'll see the alternating series notation, sometimes you won't. The ratio test is going to work on all of that. So the instant you see a factorial, gonna do the ratio test. The instant you see a sequence problem that looks like this, where you got a string of numbers being multiplied together, gotta do the ratio test on that problem right there. This one maybe not as obvious, but notice how there's like a combination, like a normal thing, like a polynomial type of thing, and then like something raised to the n power, like just a combination of things there. The ratio test is gonna work really well on that thing as well, okay? So the good news is, you got these absolute value bars, right? Absolute value bars, we know that just makes the stuff positive, which means if you have anything in there that makes it negative, you can just ignore that. And so what you're gonna see me do, because your ratio test and the root test have the absolute value bars in them already, you're going to see me just ignore the part that makes it negative. If you put that notation in your problem as you're working out, then you have to bog it down. You have to include the absolute value bars, which is making that stuff positive anyway. So what you're going to see me do, and anytime I see that, instead of writing the absolute value bars every single time, I'm just going to ignore the part of the problem that makes those negative terms in there. All right, so that's how I'm going to model this for you. So just kind of model that in your homework there, because if you're doing that wrong, you get your signs wrong, that's going to change what your answers are, and it's going to mess up your converge and diverge, right? So you're going to do limits and approaches to infinity. When you see those things, you know, like the direct comparison, the limit comparison, and integral test, you can't use those on an alternating series, but we can use that alternating series. So if it looks basic and you see that notation, use the alternating series test. But if you see factorials, or like I said, that sequence of numbers there, use the ratio test on those problems, whether it's an alternating series or not. But what you're going to do a limit and approach to infinity of a sub n plus 1 over a sub n. That's the n plus first term over the a sub n. And just like we taught you in the alternating series video, the a sub n plus 1, what I want you to do for that, you're going to replace the n with an n plus 1. That's just the next term in the sequence, the next term in that pattern right there. And then if you get an answer as less than 1, that's going to converge. If you get an answer as greater than 1, that's going to diverge. And it helps me to remember that because like infinity is greater than 1. So if I get it like infinity or greater than 1, you know, that's going to be diverge right there. That's what diverge means. It's not going to narrow down to a sum. It's going to keep getting larger, go to infinity or negative infinity. If it's equal 1, then it's going to be inconclusive. All right, so let's just go through a couple examples here with the nuts and bolts, all right? So I'm going to use the ratio test on all these examples. Let me zoom out just one time here, get a little extra space going. All right, so here's what we're going to do. We're going to do limit as n approaches to infinity. And we're going to do a sub n plus 1 over a sub n. And then, so the a sub n plus 1 is you just replace all of the n's with an n plus 1. So that'd be n plus 1 cubed over 2 to the n plus 1. And then I'm going to divide it by the a sub n. So I'm going to have this giant fraction bar. The a sub n is your original problem, not including anything that would make it alternate there. So your a sub n is this right here. Now you're going to do so many ratio tests. I'm not going to make you write it like that every single time. What I would encourage you to do, you know you're dividing two fractions here. Now, sometimes you won't have two fractions. You just have a single top and a single bottom, and you go straight to that, right? The n plus first term over the nth term. But if you have two fractions, I'm going to allow you to jump straight to this step right here where you multiply by the reciprocal already. You're going to see me model that for you on the next two examples that I do. So I would go straight to here. I'll do the a sub n plus 1. And I would divide that by the original. And you divide it by the original, you're going to multiply it by the reciprocal. All right, so you come straight to this right here. Now we just got to work on this limit. Students usually like this ratio test. It's a systematic approach and it's algebraic approach, and we seem to be strong with our algebra here. So what we're going to do, you do not need to multiply all this out. That n plus 1 to the third, we're not going to multiply that all out. But a lot of times you will see this in a problem like 2 to the n plus 1. You can rewrite that as 2 to the n times 2 to the first, because you have the same base there, right? So you would add up those exponents. That's the same thing as an equivalent. But a lot of times you'll see that. So you rewrite it like that. And then these 2 to the n's will cancel out. Sometimes you'll have something that you could do with these two items as well. But right now we're just going to just simplify this, carry that stuff down. So you have an n plus 1 to the third on the top. And then you have a 2n to the third on the bottom. And we're just going to evaluate that limit. And so if you were to multiply it all out, you have an n to the third on the top, followed by a bunch of stuff you don't care about. You're looking at the highest degrees as you're approaching infinity. And on the bottom, you have this 2n to the third. So since those degrees are the same, your answer is going to be those leading coefficients. Your limit answer is going to be those leading coefficients. And then you just have to have your test memorized. Like I said, half of the battle is just memorizing what your tests say. If you get an answer that's less than 1, that's going to converge right there. So since this is less than 1, we're going to get converge. And then the test that we're doing, we are using the ratio test. Practice this. This will not go away. This is a real important test, and it works in a bunch of different scenarios for us there. So, and like I said, students usually like this, and we usually like nail that ratio test when we're doing any sort of assessment. All right, so again, the instant you see the factorial in the problem, going to do the ratio test. You should like that because there's not even any thinking involved. You see that, instantly know comfort level that I'm going to do the ratio test here. All right, so let's do the ratio test. We're going to do a limit as n approaches infinity. I'm going to do, so thing is, that's an alternating series. The ratio test works on alternating series. If you put that notation in there, then you have to put the absolute value bars in, but it's unnecessary because the absolute value bars are making that stuff all positive anyway. So what I'm telling you is just to ignore that when you're doing the ratio test and the root test. This will be what we're working with here. So the a sub n plus 1, you're going to replace those n's with n plus 1. So when you replace that n with an n plus 1 and distribute, you're going to get a 2n plus 2 factorial. And then replace that n with an n plus 1. That's your a sub n plus 1. That's your n plus first term. And then you're supposed to divide it by the original problem. Now, the original a sub n is that just that positive part. When you divide it by the original, remember that's the same thing as multiplying by the reciprocal. So like I said, you're going to do so many of these, you're going to want to jump straight to that step right there. And then now this n plus 1 to the fifth over n to the fifth, this is just like the cube stuff over here. We're not going to mess with that. I'm not going to multiply that stuff out. But if I did have like the 2 to the n plus 1 over 2 to the n, then you might have to simplify a couple things there. All right, so what we are going to simplify are the factorials. So remember like factorials from last year, like 4 factorial, that's 4 times 3 times 2 times 1, right? You multiply each time, and each time you decrease that number by 1. So when I do a 2n plus 2 factorial, that's going to be a 2n plus 2 times a 2n plus 1 times a 2n times a 2n minus 1 times a 2n minus 2, dot, 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 all the way down to 1, right? So I'm multiplying it each time, and each time I'm decreasing that number by 1. But see, when you get to this 2n all the way down to 1, that is 2n factorial. And so now you have a 2n factorial there and a 2n factorial right there. Those two items will cancel out, and let's carry everything else down. That n to the fifth is still there, right? And on the bottom, all we have is the n plus 1 to the fifth. And remember, we're doing the limit as n approaches infinity here. And so you're just concerned with the highest degree. So you have a 2n times 2n, that's a 4n squared, times it by the n to the fifth. So that's going to be a 4n to the seventh, followed by a bunch of stuff that you don't care about. And on the bottom, if you were to multiply it all out, you have an n to the fifth, followed by a bunch of stuff you don't care about. Now remember, once you do the limit as n approaches infinity, we're using our pre-calc shortcut. So here the degrees are the same. I can use the leading coefficients. If the degree on the bottom is larger, that answer is 0. If the degree on the top is larger, that answer is going to go to infinity, because that's really like a 4n squared. So limit as n approaches infinity, like a 4n squared graph. As you approach infinity, you're shooting up to infinity. So since you get infinity, that's okay. Infinity is bigger than 1. So we're going to get diverge for that. So we're going to get diverge. And the test we're using here is the ratio test. I want to stress again why it's important to know what your tests say. Because here, remember when we're doing that limit comparison test and we get a infinity for that answer? That's not good. That's inconclusive because of the limit comparison test. You're looking for a finite positive number, and so infinity would be bad if I'm doing a limit comparison test. That doesn't help me. But here, if I get infinity, that's bigger than one. That actually helps me. I'm going to get diverge right there. All right, so there we go with the ratio test, man. I am so hungry right now. I woke up at 4 something in the morning today, been making videos all day. I'm making 10 videos today, and then I'm done. I got this one and one more, and I'm done, like done, man. I'm so hungry. I'm getting that oven warmed up, man. Gonna get that frozen pizza going. That's what I'm about to have in a little bit here, man. It's gonna be good. All right, so let's do one more problem. Usually I leave this example off of the notes, but each year I leave it off of the notes. We always have questions over it the next day as we're going through homework problems there. This is not the same thing as a factorial. This is not 2n minus 1 factorial. You're not subtracting 1 each time. This is also not the same thing as if I just have 2n minus 1 over 3n minus 2. Those are two completely different problems. This is a whole string of numbers that you're multiplying together on the top, like 1 times 3 times 5 times 7. This is 1 times 4 times 7 times 10. That's a whole string of numbers that you're multiplying together on the top and on the bottom. Now, a lot of the problems, you might not have it both in the numerator and the denominator. You might just have one of them in there. But the instant you see any of those in there, that's a ratio test problem. And it doesn't matter whether I squeeze in that -1 to the end notation there to make it alternating or not. It doesn't matter, okay? So I'm just gonna kind of ignore that for now. But if I did, I would just ignore that and ignore the absolute value bars, okay? But let me show you with you how to handle this sequence problem, right? I really like these. These are pretty easy there. When you just do what I tell you to do real quick, it's going to be perfect for you. All right, you're going to do a limits and approach to infinity. Now, when you do this a sub n plus 1 part, here's what I want you to do on a sequence problem, is I want you to rewrite everything that you have in that sequence. Rewrite everything that's there, and then we're going to add on an additional number. We're going to add an additional term, the next term in that pattern. Now, there's two ways that you could do that. Is you can replace that n with an n plus 1, right? I told you that'll always work there, so that's always going to work, right? So if you do that, that'll be a 2n plus 2 minus 1, which will be a 2n plus 1. That's one way you can do that. That's what I'm going to write right here is the 2n plus 1. Another way you can do that is to recognize the pattern. We're trying to add on the next number in that sequence there. So 1 times 3 times 5. So yeah, you're adding 2 each time. So to go from this term to this term, from this number to this number, if I go to this and I add 2 to that, I do a little plus 2 right there. -1 plus 2 gives me that positive 1. I think it's a little bit quicker to just recognize what you're adding on each time. So that's what I'm going to do on this next one. So I'm still working with that a sub n plus 1. There's the top part. The bottom part, again, when you do the a sub n plus 1 on this sequence problems, I want you to rewrite everything that you have there, including that 3n minus 2. And I'll talk about why in a second. And then you're going to add on the next one in that pattern. So the quickest way to do that is to realize you're adding 3 to get from the 1 to the 4 to the 7, to get from this one to the next term, you're adding 3 each time. So if you go to this one, you put a little plus 3 right there, -2 plus 3 will give us a 3n plus 1. Or like I said, what will always work is if you replace that n with an n plus 1, that'll give you a 3n plus 3 minus a 2, and that'll give you the 3n plus 1, the same thing that we're getting right there. This right here is your a sub n plus 1, okay? Here is the common mistake, is students don't listen to me right there. They don't do what I just told them, and they don't rewrite what they have there. Sometimes they ignore the numbers altogether and just act like it's that, and then that messes them up. Here's the most common mistake, though, is they know they need to write the string of numbers. So they write the 1, 3, and 5. They won't include the 2n minus 1, or they won't include the 3n minus 2. And so let me just prove to you, like, why that doesn't make any sense there. So, like, look, if one of your terms on the bottom is like 1 times 4, the next one would be 1 times 4 times 7. The next one would be 1 times 4 times 7 times 10. And you get the idea. The next one would be 1 times 4 times 7 times 10 times 13, right? That's what we're doing. There's the first term, there's a second term, there's a third term, there's a fourth term. Each term that you add on, it just adds on another number that you're going to multiply by. So if you don't include the 2n minus 1, that's, or the 3n minus 2, that's like going 1 times 4 times 7 and skipping over the 10 and going to the 13. Doesn't make any sense there. You just messed up the problem right there. So that's why you need to include everything that you have, then add on the next one. Include everything that you have, then add on the next one. That's what that whole sequence is, because it's a whole string of numbers that you're multiplying on the top. It's not a factorial. It's not just a expression over an expression. It's a whole string of numbers that you're multiplying out there. So technically you don't need to write it, but if you don't write it, you got to understand that is the term that's right in front of that, so it's in there. But most of the time, the people who don't write it, they don't see that something cancels out like they're supposed to. So I would be safe. I would always write down whatever you have there and then add on that next term in that pattern there. So that's your a sub n plus 1, and now we're going to divide it by the a sub n. This is my a sub n. So when I divide it by the original problem, I'm going to multiply it by the reciprocal right away. And you have to show me this step. You can't do stuff in your head in this chapter on these problems right there. You have to show me what you're taking the limit of, and then we can do our algebra. Then we can do our limit. Then we can do our pre-calc shortcuts. But you got to show me what you're taking the limit of, right? Because limit comparison test, you're doing a limit of something different. Ratio and root test, you're doing a limit of something different. The nth term test, you're doing a limit of something different. You got to show me what you're doing first, and then we go with our simplifying. You can't just do a bunch of stuff in your head right there. All right, so show that step. There's my a sub n. So I multiply by the reciprocal, right? And now you could cancel stuff out there. It's real easy, okay? So you're just gonna cross those out. You can cross all these out. And all you're left with now is the 2n plus 1 over that 3n plus 1. And then you always have to do that the right way, because there's weird things that happen. Sometimes we'll combine that. You only have one sequence, but then you got a weird power or something on the bottom. Maybe you got a factorial on the top, right? And so if you don't do it like this every single time, you might get lucky occasionally, but if you do it like this every single time, you're going to get it right every single time, unless you just make some little mistake right there. But there's some weird things happen that if you don't do that stuff like I'm asking you to, it's going to mess you up and you're going to get that wrong answer there, right? Now, make sure you gather everybody. Make sure you don't miss anybody. Cancel everything out like you're supposed to. Now we're going to do limits and approaches infinity of this thing here. The degrees are the same. We're going to get 2/3 for that. 2/3 is less than 1. And so since I get less than 1, we're going to get converge using the ratio test. Simple. Practice it. Be good at that. That's a really important test there.